This is Doug, and welcome back to Break Tech. We're going to finish up our tic-tac-toe application by adding the AI in this video. We're going to use an algorithm called the MiniMax Algorithm. If you haven't watched the previous video, go check that out. I'll try and link it. But essentially what we're going to do is we're going to create a function which evaluates the state of the board. It's going to assign a value, either a high value, a low value, or a zero or null value, to each end node of that tree. It'll award a high value if the maximizing players wins a game. It'll evaluate to a low score if the minimizing player wins a game on that particular node, and it'll evaluate to 0 if neither player wins. We'll alternate back and forth between players. Each player alternately, one tries to maximize the end value, one tries to minimize the end value. And that's pretty much where we need to go. So we need to add some state values. We'll have the winner, we have the turn of the player who starts, but we'll need to add a max player, and that'll be X. And we'll need to add a min player, and that'll be O. And this will just be so we can evaluate each time we run the algorithm to see whether or not it's the min or max player we need to be evaluating for. And we also need to update our, we can just copy these. We're going to update our reset board. In the same manner. Otherwise, when we reset the board, the min player and max player won't exist anymore. So that pretty much takes care of the additional state we need to manage. Now there are a few things I changed. I changed I changed a lot when I was doing this. I optimized it somewhat. I found, and this isn't my implementation, I found an implementation of the winner function, a function to evaluate who won the game, that I liked a lot better than the way I was doing it. I was doing it with just a ton of code, and you can see here that I let the I made a copy of the current game board, and then I spliced in the turn, and then I evaluated. This is my evaluation for who won, and I didn't do it in a separate function either, so that's something we'll improve here. I evaluate each one individually with using regular expressions, and while it works fine, it's just super complicated and extremely long. Also, I ran into some problems when I was writing the new algorithm, in that I was having problems with the set state being run asynchronously, and essentially trying to update the state before the game board was actually changed. So this will also fix that. So what we're going to do is I'm going to go ahead and I'm going to take out this update board function. Oops. Right here. And we're going to replace it with a few different things. So I'm going to create a function which evaluates if there's a winner to the game. And it takes the board, and then it also takes a player, which player's turn it is. And then we'll have an if statement. And this is sort of the meat and potatoes of this function. And this is, again, not something I wrote. I found this and I was like, oh yeah, that's way better than what I did. So we'll check the board in location if 0, and so this will be the top row we're evaluating. And the cool thing about this function is that you can just pass X or O, whoever's turn it is, and evaluate this, and you have a lot less logic that you need. And we can copy and paste here in just a second and create the rest of these. So board 1. Oops. So if position 0, position 1, and position 2 equal player, then we have had a winner, and then we'll just say or. So that's our top row. We'll do our middle row, which would be 3, 4, 5. And then we'll do the bottom row, which would be 6, 7, 8. And then we need to do the columns. So first column is 0, 3, 6. Second column is 1, 4, 7. This will be the middle column. And then we have the third column, which is 2, 5, 8. And then we have the two diagonals. So we have 0, 4, 8. So the diagonal starting in the top left corner. And then we'll have 2, 4, 6. The diagonal starting in the top right corner. So if any of that, we'll just return true. Oops, can't type. Or we'll return false. Actually, I returned null. Not sure if that was important. I did that on purpose, so we'll go ahead and do that again. All right. So then, in addition, so copying the board becomes important, and the reason it becomes important is because of what I was talking about before with the asynchronous calls to set state. So we never want to work on the state itself. So what was tripping me up was what I want to do is I want to grab the player's move. I want the player's move to be evaluated to make sure that nobody's won. Well, I want to make sure it's valid. Then I want to make sure that the player didn't win. If the player didn't win with that move, I want to run the AI script, and I want the AI move to be placed as well. But the problem is I can't run a set state on the board and place the player's move, and then run a set state on the board and place the AI's move, and then return to the player. What I need to do is take a copy of the board, add the player's move to the copy of the board, evaluate the copy to see if there's a winner. If there's not, go on like I said before, and then evaluate the AI's move, add the AI's move to the copy, and then only have one set state call that I'm going to run at the end that's going to update the board with both moves. So that's sort of where we're headed and why we're doing it, why we had to make some changes. So copy board is just a function to copy the board. And that's it. That's the entire function. So it's just to make sure we're only manipulating the copy, not the originals. And then this is something we were doing inside of the same function, the same update function as well. We're going to take this valid move and determine if a move is valid, which is something that AI needs as well. So it came out pretty useful. So we pass in the board, we run our copy board function, creates a new board, and then we say if the new board with the player's move is equal to just a space, then we'll go ahead and assign the move. And we'll assign it to whoever the player is, and then we'll return the new board. So it doesn't just check if it's a valid move. If it is a valid move, it also places the move on the board. And if not, well, we'll just return null. All right. So now the AI needs to find itself a move. So we'll write a function called find AI move, and it takes in a board. We're going to say the best move score is 100. So the AI is, so the way it's written, the maximizing player is the human player, and the minimizing player is the AI. So the best move score is just an arbitrary high value, so that the AI score is below it when we evaluate the board. I'm trying to use let a lot more than var, but you can see now I'm mixing. I don't know. It's like a really difficult thing for me to get across is to use null. I'm sorry, to use let rather than var. So we're going to test every possible move, and if the game is not already over. So and the way we're going to do that is we're going to say if this dot winner, so that's that function we just wrote, pass it a board and x, or so if x or o has won the game, or there's a tie, we want to just go ahead and return null, because we don't need to place a move. The game is over. We don't need an AI move. I just found a typo in my original, but for some reason it didn't break the code. Which probably is a bad thing, and probably means that my function was never being evaluated. But anyway, let's carry on. All right, so now we go into our for loop. So this will be the first for loop of the recursive algorithm. So start with var I equals 0, and then I is less than board.length. What we want to do is here we want to say let new board equal this dot valid move I this dot state dot min player and board. All right, so what are we doing here? So far what we're doing is we're going to check every possible move that the AI could make, and we're going to see if it's valid. If it is valid, we're going to go ahead and return a board. And then what are we going to do? We're going to call the function again on that. We're going to call the minimizing or maximizing function again on that board if it's valid, to see if that is a better move. So if it is a valid move, what do? We want to say if new board. So if new board exists, that means it was returned and it is valid. And now what we're going to say is, so we want to assign a move score, and it needs to be the maximum of all of the move scores that we get from positions that we test. And we need another if statement inside here, and we say if the move score is less than, and this is because the AI is the minimizing player, if the move score is less than the best move score, we want to replace it with the new move score. Oopsies. And we want to keep that move as well, because so we want to capture the iterator is going to go through the whole board. It's going to find each valid move. Each valid move is going to be a value of I. So we want to assign I to the move that we're going to use at the end to actually place on the board the AI's move. We're going to save anything that has a better score than the best move score. In this case, move score, if it did end up being better. And then we want to go ahead and at the end of this whole thing, we want to return whatever move we decided was the best move. Alright, so we're not quite done, because now we need to evaluate this max score. We need two more functions. We need the max score and the min score. And you can do this in a single function, but this to me just made more sense. Because you can pass in which it is, the min score or the max score that you're looking for, instead of having two functions that basically look the same. But I got it working, and that's what I was hoping for. So in this, the min score, we'll say this dot, if this dot winner board X, we want to return 10. And what we're doing here is we're setting the maximum value for any board state, any end node where X is the winner. We want to give it a high score. So we'll go ahead and return that high score, which is 10. Now, if this dot winner board is equal to O, that's the minimizing player. And in those cases, we want to return a low score or -10. And if we end up with a tie, in those cases we want to return 0, which is just an intermediate value in between 10 and -10. So it'll be a higher score. For the maximizing player, it's going to be a higher score than -10, and for the minimizing player, it's going to be a lower score than 10. So it's just the intermediate value. Alright, so if there's a winner or there's a tie, that means the game is over. We want to return a value. If it's not over, we need to keep going deeper into the tree. So else we need a var best move score equals 100, and this is where, you know, it could easily be refactored to be less lines, because I'm using 3 functions where I could probably have used 2. It's not really equivalent to find AI move, because it returns an actual move, not another board or a value. So probably I could have had 2. I could have had a minimizing maximizing function that just took in which player's turn it was, and then did the same thing. And maybe I'll fix that eventually, but for now I'm not going to change it. Alright, so, and this will be very similar to what we saw above, except rather than using the max score, we're going to use the min score. get a new board. We're going to pass in this particular location on the board. We're going to pass in the min player and the board. And then if it's valid, this is very similar to what we did before, almost exactly the same. Take a predicted move value equals this dot max score. And say if that predicted value is better than the best move value, we'll replace it. I actually use best move value in this version. And predicted move value, so I'm going to go ahead and change that. Which shouldn't make any difference whatsoever. But so predicted move value is less than best move value, then best move value equals predicted move value. And we'll return the best move value. So this is the value that our original function is going to evaluate every time it receives a score back from the algorithm. Whether it's when it's evaluating an actual move, it's the score. So this function returns a score, and this find AI move returns a move, an actual board position. So now we just need to change this to evaluate for the max score, which, like I said, could be one function. Well, that's not how I wrote it, so we'll just say, we'll call this max score, and then we'll do kind of the same thing. The only thing that's going to change is the best value is going to be not 100, but negative 100. And this will change to a greater than from a less than sign. And then we'll again want to call the min score, not the max score. But the scoring of the board is the same. We want a high score rather than a low score, so we change this to an arbitrary low score. There's no difference in the for loop. It's evaluating each possible board state with a move, and then finding out if that move ends the game, and then evaluate and returning a score. All right. So because we took out our update game before, I also need to add a game loop. So we'll call this game loop move. Game loop receives a move from the player on the board, and this will say let player equal this dot state dot turn, and then let the current game board equal this dot valid move player this dot state dot game board. Excuse me. So if this dot winner, so we are evaluating now to see if our player's move won the game. So this is outside of AI. This is just evaluating the player's move to say, hey, did the player win with their current move? First, was it valid, and now did they win? And if they did win, then we want to go ahead and update the state because the game is over and the AI doesn't get a move, so it doesn't matter about we were talking about earlier about the synchronicity of the moves being updated on the state. So we'll say this dot state. This dot set state. And we'll say game board will be current game board, and winner will be player, whoever's turn it currently is. All right. And then we can go ahead and just exit. So now we've checked to see if the player won. Now we need to see, is there a tie? Oops. And if we tied the game, the same thing as before. I guess actually we probably can just take it all. So we went ahead and set a draw as just the D character, and that's something we had before. So if this dot tie current game board, if there is a tie, we want to set the state. So the game board is the current game board, the winner is a draw, and then we return and exit again. And then we want to say, okay, so if not, we want to change the player over to O and let the AI take a turn. So we'll say current game board equals this dot valid move this dot find AI move with the current game board, and we'll pass the player and current game board. So now the AI takes its move using the find AI move. So we need to find out again if there was a winner. And we'll pass the current game board and the player. And if it was, then we want to go ahead and do the same thing we did up here. Only this time player is already set to O, so we don't need to do anything different there. And then after checking for a winner, we want to check for a tie. Oops. So if this dot tie current game board, and then same as here, go ahead and set the state as the current game board and the winner as a draw. And if neither of those things, that means we need to go ahead and return play or control the game to the player. So the only thing we need to update is the board, because there was no winner, there was no draw. Ooh. Pretty sure I need to go capitalize all those. I'll make sure here in a second. And that is it. That's the only thing we need to update in state. Because we've used the same current game board is our copy of the game board that we've been using the whole time through both the player's move and through the AI's move. Now we just need to update the state one time and both moves will be added. So to the player as they're playing, it'll look like they're added basically simultaneously, which shouldn't really matter. It doesn't affect play. I guess we could put a delay or something just to make it appear, I don't know, just to make it appear like the AI is working a little harder than it is. So these game boards that I've put in here should all be capital B. Because that's how we set it in the state. Now we just need to verify that everything in our functions have changed and what we're calling has changed. So we need to pass in as a prop a different function for our. We need to pass the game loop so that when the player makes a move, they can actually call the game loop. So we'll go ahead and just make that quick change because now we're still using the key, the location, the value, but we're not calling update board and we're not using turn. It's something we actually weren't using anyway. So we want to just call game loop here, and we'll go ahead and pass in this dot game loop dot bind this to verify that we call that this when we call the game loop is called on app.js's function rather than the tiles function when we're actually using the tile component. And I believe we made some changes to the tile as well, so let me pull that up. So in the tile, yeah, so we need to change this to game loop, and then props.look and props.turn are the same, and then we need to say, I think our onClick remains the same. This .Kyle click, this .props, this .props .value. Yep. So everything else should be good. So we'll go ahead and save that. And that's been a ton of code without testing anything. So let's go ahead and see if we can't pull up our console and test it. Oops. All right. So go to desktop, my web projects. I think can't remember what I'm in. I'm in Tic-Tac-Toe. So we'll just start that up and see what kind of errors we get. I'm sure I have at least another couple. Oh, there we go. It's even launching. All right, so we do get it to launch, but nothing's coming out. Found a couple of problems. One, so line 138 of the game loop, where I was having problems spelling game board before, I did it again. So this should be this.state.gameboard with a capital B, and that will make sure that when we call valid move, we're actually using the state of the game board that actually exists. Otherwise, when we call valid move, it calls copyboard. Copyboard gets an invalid or a non-existent game board, and undefined object. So that's one thing. And then the other is we forgot to write the tie function at the beginning here. So I have my winner function, but I forgot to write the tie function. So if we have a tie, we pass in a board. And we take, so the way I'm doing this is I'm joining all of the array elements into a string and then removing any empty spaces. So the length of the string is the length of the number of moves that have occurred so far. So var moves equals board dot join with no space there. That is just an empty string. And we'll replace anything in there that is an empty space repeating with an empty string. And then if moves.length is equal to 9, then we know that all the moves have been taken. So we can say, yep, there is a, go ahead and return true. There is in fact a tie, and if not, we can return false. So that is 2 errors that we definitely had to fix. So let's see now if it's working. It says move is not defined. It's a reference error. I also added a console.log that just prints out the board just to make sure that the board was actually working. So we've got, here's our error in the console. So it looks like on line 42 or 43, I used moves rather than move. So let's go and fix that. Actually, I think I do want an S there. We'll call it moves. So we'll go and check that. All right, that looks fairly infinite. So we'll go ahead and check out what's going on there. I think I know what it is. I think that we forgot to take out, I think there's one more change in the max there that we didn't take out. And then our max score function should be, this should be max player, not min player. That probably is our error. Go ahead and see if that did anything. It looks like we now have a working tic-tac-toe game. It looks like O beat me. Now here, O had to block, so I can go here. They had to block. I can go here. They have to block. I can go here. Tie game. Okay. So that concludes the MiniMax algorithm and our tic-tac-toe AI. If you're interested in me going through the deployment of the application to the web, let me know. If not, go ahead and check out below. I will have a link to where I have the live app up on my blog. And if there's any other comments or concerns, or if there's anything else you'd like me to show or explain better, because I know I went through this pretty quickly and then had some errors at the end, just let me know, ask questions below. I really appreciate it. Please hit like and subscribe if you enjoyed this video. Thank you.